The content of this video, as well as the thoughts, views, and opinions expressed herein, belong to the presenter and do not necessarily reflect the views of Brigham Young University or the Church of Jesus Christ of Latter-day Saints.
Well, I'm very impressed that so many of you are willing to come at this late hour in the afternoon. You're probably tired. We're going to have some fun today talking about light. Let's get on with it. Light in science and theology. So we're in the midst of a discussion of the interface between science and religion. Yesterday, we talked about the cosmos on its largest scale, and we decided that modern science and modern revelation have recently come together in one truth, and that is that God's universe is beyond comprehension in scope and grandeur. And we illustrated that with some interesting examples. Today, we're going to talk about another area of study that overlaps between science and theology, and that is light. Light is important in many respects to all of us because it is how we observe the world. Now, in history, if you wanted to make artificial light, you had to heat something really hot so that it would glow, like a fire or a candle or something like that. And in fact, this has actually been true right up until a couple of decades ago, when we started transferring over from incandescent lamps to LED lamps. These incandescent lamps that we were using for most of my life, and maybe much of yours, only converted about 10% of their energy to light. The rest, the 90%, was just converted to heat, as anyone knows who ever tried to touch a light bulb that's been on for very long, right? Well, these new LED lights are the product of the science that we've been studying in chemistry and physics for a long time, and finally came up with a way to produce light in a much more efficient manner, and that gives us a lamp that is 80% efficient, 80% light versus 20% heat. So that's some serious progress. But you know, nature has been producing light that gives off virtually no heat, not completely, but almost no heat, from time immemorial, in the form of fireflies, for example, and these bioluminescent algae that you find sometimes in the ocean. This process is called chemiluminescence. And we have been able now, over the last several decades, we learned how to produce this kind of non-heat producing light in the form of chemicals like luminol, which I'm going to illustrate for you now. But before I do, I have to don my scientific garb, prepare myself to enter the realm of true science. So luminol is a fairly common chemical process that is used in forensic chemistry. And I'm going to ask the students to turn the lights off, if you wouldn't mind, as we do what chemists are famous for doing, right? And that is mixing one chemical with another. And we'll see some magic. Before the advent of these glow sticks that kids use at Halloween time, this was actually a very awesome demonstration. Anymore, I guess it's not quite so surprising to you that this happens, right? But still, I'm going to ask for some voluntary input here from someone in the front row. Anybody want to volunteer? Okay, just touch the bottom of that flask and tell me if it's hot or cold. It's just cold, right? So this is a process that produces light without generating any heat at all, or virtually none. So there are ways now, and maybe in the future we'll have lamps in our homes that produce 100% light and no heat at all. But we've made some real progress, haven't we, just in the last few decades in this way. And I think it parallels progress we've made in many other ways as well, especially for those of us who've had to spend thousands of dollars keeping up with the phone progress that happens about every year. Got to have a new phone, right? Or your grandkids need a new phone, at least. This is all in keeping with that hymn from the dedication of the Kirtland Temple that we talked about yesterday. William Wines Phelps wrote that the veil or the earth is beginning to burst. And as we illustrated yesterday, that is really true when we think about how we look out into the universe at large, and now we see a universe that is completely different from anything that anybody saw just 100 or 200 years ago. A universe that is filled with innumerable stars and galaxies. But this is also true in the realm of the very small. And so we could maybe modify Phelps' poem just a little bit and say the veil over all of nature is beginning to burst. And it's as if we had some kind of a covering over our eyes when it comes to deciding what is happening on the small scale in the universe as well. How does this come about? Well, it comes about in part through revelations through prophets, but it also comes about in part from revelation to all of us and scientists among us. In fact, Brigham Young made the point that every discovery in science and art that is really true and useful to mankind has been given by direct revelation from God, though but few acknowledge it. It's been given with a view to prepare the way for the ultimate triumph of truth, and we would say, and the reign of our Savior on the earth. So we all are beneficiaries of this kind of revelation at one level or another, and we all benefit as we share with one another. Now, traditionally, as people in science, and you and I, have tried to look at the world and come to understand it, we have done so with our eyes. And our eyes are rather limited in what they can perceive in the universe, as William Phelps' poem kind of captures. If we look out into the sky, we see the stars. If we look down to the earth, we see living things, and we see all the mountains and the formations on the earth. But this is all done with the light that can come to our eyes and what our eyes allow us to understand through our thinking processes. But you know, in recent years, and by recent I mean in the last few centuries, we have come to see nature, the universe, the world, in two new ways that had never been available to mankind before. To begin with, we have been able to look at things from the perspective of a different magnification, if you will. First of all, from the invention of telescopes back in the early 1600s in the Netherlands. This was the same kind of telescope that Galileo used to find those little planets, those moons circling Jupiter. And over the years, we've improved on those telescopes and built bigger and more elaborate ones like the Hubble telescope that we saw. But they're all looking at the world with the visible light that you and I can see with our eyes. Same is true with microscopes. Those were developed at about the same time in the same place. But over time, they have been improved, and we can see further down, if you will, in size. We can look at very tiny things with the most powerful visible microscopes that we use today. And this has been another way that we have been able to push aside the veil that was covering our ability to see the world as it really is. But there's another one. And that is, we've learned in the last couple of 100 years to make use of light that we didn't even know existed before that time. You see, it was in the 1800s that the spectrum of different kinds of light that we now take for granted exist were being discovered. Before that time, things like ultraviolet light, infrared light, microwaves, and radio waves just weren't available. The only thing people were looking at, seeing, perceiving was the range of visible light that we consider in the rainbow, this range of wavelengths of visible light from the purple to the red. But gradually, over the last couple of 100 years, we've come to understand that there is a huge range of different kinds of light, ranging from gamma rays, X-rays, ultraviolet, infrared, microwave, and radio waves that, as I say, before that time, nobody knew even existed. This diagram orders these different kinds of light according to energy, the higher energy ones being things like X-rays and ultraviolet light that give us sunburns, and infrared light and microwaves that we use to heat our dinner, and so on. So this is another way that the cosmic veil is being drawn back, and we can see into nature in ways that couldn't be seen before. Some of the advantages, let's look at a few examples of some of the advantages that we have gleaned from being able to take advantage of these other wavelengths of light. The James Webb Telescope that was just launched not too long ago actually doesn't look at visible light very much. It looks at infrared light. Now, infrared light is slightly less energetic than the narrow range of visible light that you and I can see with our eyes. And so the Webb telescope is able to look through, using this infrared light, through the kinds of dust and gas that constitute these clouds in the pillars of creation, so-called, that we looked at yesterday, that are about 7,000 light years from us within our Milky Way galaxy. And you'll recall that we talked about how this kind of cloud, and there are many clouds like this in the galaxy, is where new stars and solar systems are being born. Just to give you a sense of the scope of the size of this cloud, our solar system itself would fit in that little button right there on the end of that cloud. This is one example. Here's another example. This is a radio telescope, believe it or not. All these radio receiver dishes add up to one telescope. It's in Chile, and it looks at radio waves. And with looking out into space with this kind of telescope, we can see something else that's really impressive to me. In 2014, this telescope was used to take a picture of this structure here in one of the gas clouds I was just talking about. It's 450 light years away from us, and this is a new star being born. And around that star, you can see the detritus of this collapse of the new star that is going to be collapsing itself into individual planets. Now, this is essentially visualizing, actually seeing, if you will, not in visible light, but in radio light, the formation of a baby solar system. This is our Heavenly Father at work. You're looking at it right now with your eyes. And I want you to understand that this is not a computer simulation, okay? We are so used to going to the movies and seeing simulations of stars and people in spaceships traveling from one planet to another. That's not what this is. This is an actual photograph of an actual solar system actually being born. Did I use actual enough there? I think that's just kind of, well, very thought-provoking. Okay. Also, we have telescopes that can look at microwaves. And these microwaves have revealed to us the pattern of light that comes about as a result of the Big Bang. we could spend a whole day talking about this. Well, obviously we don't have time, but just so you know, these microwaves are the echoes, so-called, of the Big Bang, and show us the structure of the universe at its very beginning. At the beginning, these photons of light were very energetic, and so they would be maybe in the gamma ray range. But as space itself has stretched over the last 13.8 billion years, the light itself has stretched. And if you know what I'm talking about when I say wavelength, it means that the wavelength of the light has stretched, and it has converted from gamma rays to microwaves at this point. Okay, so this is a picture of that. I show this in part because this microwave background radiation has made it possible to see what's happening at the beginnings of creation if the scientific model is correct. And I just make you aware of this interesting book by Gerald Schroeder, The Science of God. In his chapter 4, he provides an interesting way to correlate the science-based creation story and Genesis 6 days. I know this is something that is of interest to a lot of people. Most of us have asked the question, what about the creation? You'll notice that I don't go into that topic in this series of lectures, in part because it would take a series of lectures all by itself to make any dent in the question. It's a very interesting question, so I recommend that you take a look at this book if you can get a copy. It is, I don't agree with everything that he says. He's not LDS. He comes at it from a Jewish perspective, and that's not a problem. But this particular chapter provides thought-provoking insights, I think, into this question. So I'll leave it to you. You can find the answer to that question, and you can teach a class at Education Week about that. So in the latter days, science and religion have come to reveal to us amazing new insights into the nature of light that I'd like to spend time talking with you today about. These insights provide us a key, I think, not only in science, but in religion as well, to understanding our Heavenly Father, our own place in the universe. In fact, as we look at the scriptures, we find that they are full of references to the word light, to the concept of light. You knew that already, but you might be interested to know that there are 453 references to light in the scriptures. That's quite a few. And just as an example, some familiar verses. I am the light of the world, says Jesus. He that followeth me shall not walk in darkness, but shall have the light of life. Jesus was the true light, which lighteth every man that cometh into the world. You'll find lots of references to light in the book of John. And of course, in our latter days, we find that light is, it permeates all of the revelations of Joseph Smith and the visions that he had. Just to capture one here, he says, I saw a pillar of light exactly over my head above the brightness of the sun, which descended gradually until it fell upon me, and so on. So our God and all the, Christ and God and the angels and so on, they're beings that we associate with light, aren't they? We think of light in every case. I'd like to spend the rest of our time talking about a couple of subtle but profound parallels between modern revelation and modern science as it relates to light. So here we go. Let's ask first the question, what more has science learned during the fullness of times about light? Well, let's go back into history just a little bit, because it's hard to put into perspective what we know about light without understanding how we got there. In around 1700, this man, remember his name? Who's that? That's Newton. Proposed that light was made of particles. And his counterpart over in the Netherlands, Christianus Huygens, taught that light was a wave. And this competition between the modeling of light as a particle and modeling light as a wave went on for quite a while, even after these gentlemen passed on. And in fact, it wasn't until about the time of Joseph Smith, actually it was after Joseph Smith's death, that the problem was essentially resolved in the eyes of most scientists in favor of the wave model of light. It was a contemporary of Joseph Smith in England, whose name was James Clerk Maxwell, who came up with a model, once again, mathematically based. We won't talk about that, but the sum and substance of it was that he modeled light as a wave. And in fact, a particular kind of wave called an electromagnetic wave. Why electromagnetic? Because it was associated with electricity and magnetism both. And he's the one who found that these two forces in nature, these two phenomena in nature, are intricately connected to one another, and that they are connected to light itself. By the way, I want you to memorize that word because it's going to be on the final exam, okay? Here's Maxwell's model. He thinks of light as a wave, okay, of magnetism and electricity going back and forth to each other. Now, you might wonder, well, what led him to conclude that it was a wave? I'm going to need my folks to come up and help me out here. So Ruth is going to come and do the same demonstration on that side of the room as I'm going to do on this side of the room so that everybody can see it. I'm going to shine a laser beam. It's blue. Can you see it at the back? Okay. You see the laser beam? It produces a single beam of light. But if I shine that beam through a diffraction grating, which some of you have, all of you have a diffraction grating, either in glasses or one that looks like this. This is just a sheet of plastic with little tiny scrapes of lines in it. So small you can't see them, but they're just as if you took a rake and raked some sand and produced a grid of lines. And you'll notice that there is a phenomenon here that we observe. It's called diffraction. You don't have to know that, and it doesn't matter what it is. But the point here is that you can't explain why this single beam of light breaks up into several beams of light when it goes through this grating. You can't explain it in any other way than to describe the light as a wave. Only waves do this kind of thing. Thank you. But the problem, of course, if you're talking about light coming from the sun to the earth, for example, is what's waving? Light leaves the sun, gets to the earth, but there's space in between, empty space. So what's waving? That problem persisted. It was not clear. And yet this model endured until somebody else came along. And I bet you know who this is. Yep. The unsettler of the 20th century in science, because he upended so many of our cherished ideas in science. You can see that he was glad to do it too. In the 20th century, an experiment was done, or an experiment was explained, I guess I should say, that doesn't fit the wave model. I'm going to demonstrate the photoelectric effect experiment to you, but to do that, I want to just remind you of a couple of basic principles of science that you learned back in grade school, just as a reminder. We're going to do the demo. You have to remember that for the demo to be understandable, like charges repel. You remember that, right? You remember that charges are either negative or positive. And so negative would repel negative, positive would repel positive. And the other thing you need to remember is that electrons have a negative charge. With that in mind, watch carefully and see what happens. This is called an electroscope. I'm going to add an electrical charge to the electroscope by rubbing this rod on this four-dead anole here, and adding the electrons that result to the electroscope like this. And you'll notice that the needle on the electroscope has moved because now both this metal and that metal have a negative charge and repel one another. Now, of course, if I were to remove the extra electrons from the electroscope, this needle would fall back down. One of the ways I can do that is to shine light on the metal, and with that light, try to knock the extra electrons off. I'm going to start by doing that with a red laser. You can see that this is a red laser beam here. I'm going to shine the red laser beam continuously on the metal of the electroscope. And you'll notice that no electrons are coming off using this red colored light. In fact, I could probably shine that red laser light on the electroscope all day long and the electrons would not come off. But I have here an ultraviolet light source, which I will now shine on the electroscope. Let's see what happens. Notice that immediately as ultraviolet light hits the electroscope, electrons are coming off, the needle is losing its negative charge and is falling back down to its original position. Now, it's this phenomenon, the so-called photoelectric effect, that Einstein explained and which won him the Nobel Prize. I probably should have added to my list of things you need to remember here is that red light is less energetic than ultraviolet light. I think you knew that anyway, right? So let's talk about this experiment and its implications. Let's go back through what happened, or at least what we were expecting to happen, and see what we can conclude. We're attacking the question, is light a wave or a particle? Now, if light were a wave, this is what should happen. If light is a wave, then energy should build up on the metal as we shine the light on the metal. And as the energy builds up higher and higher and higher, then eventually enough energy should be present for the electrons to pop off the metal, and that would allow that needle to fall back down because there wouldn't be any extra electrons on there anymore. Does that make sense? Okay. So let's see what happens when we actually do the experiment. We shine the red light on there, and we wait a while to allow the energy from the red light to build up on the metal and see if some of the electrons come off. Well, we wait and wait and wait, and nothing happens. Okay. The electrons should come off, but in fact, here we go. What I just showed you does not happen. You could shine that red light on the metal all day long, and the energy of the red photons, the energy of the red light, would not follow this idea. It would not build up in the metal and eventually cause the electrons to fall off. So that's not what happened. Remember, we saw it in the video, right? Okay. So Einstein makes the point that if light consists of particles of high enough energy, then the electrons should be knocked off immediately. Okay, let's try shining light of higher energy, ultraviolet light, on the metal and see what happens. We shine it on there and immediately the electrons come off. So that is consistent with light being particles, packets, individual packets of light sufficiently energetic to knock electrons off. So in the 20th century, we find this new result that flips us back again to Newton's original idea that light is made of particles. Einstein concludes that light consists of particles which are like individual packets of energy. Red light contains packets that are of low energy, not enough energy to knock the electrons off. UV light, ultraviolet light, consists of particles of high energy, high enough energy to knock the electrons off as soon as they hit the metal. Here's, in case you're still kind of scratching your head, let me just give you one simple analogy to this experiment. Let's imagine that we're trying to knock over an elephant. We have two possible ways of doing it. First, we could just shoot BBs at the elephant from a gun. Now, just to be humane to the elephant, instead of using a real elephant, we'll use an elephant, a statue of an elephant, okay? So we're going to try to knock the statue of the elephant over. And the first try, we're going to use a BB gun. We can shoot BBs at that elephant all day long, and it's never going to fall over. Right? Okay. Well, that's the equivalent of trying to knock electrons off with red light. The electrons are like the elephant. The red light, no single packet of energy, no single photon of energy is energetic enough to knock the elephant over. Not only that, but the energy that the BBs accumulate as more and more BBs hit the elephant does not add up. It doesn't add up that way at all for the elephant. Instead, what we're going to need is a tank, okay? And we're going to blow that elephant over with one shot, right? So I hope that kind of illustrates for you how this experiment nails the validity of the particulate model of light. Well, there's a problem here. Remember, we showed the diffraction of light here on the screen that it says that light has to be a wave. You can't explain the diffraction of light from a particle model. But now we've seen the electroscope experiment, the photoelectric effect, that shows that light must be a particle. You can't explain the result of that experiment using a model of light as a wave. So what are you stuck with? What do you do? Well, unlike anything that happens in science, usually we compromise and we say that light is both. And we'll get back to how that can possibly be in a minute, but we call this compromise wave-particle duality. We say that light acts sometimes as a particle and sometimes as a wave. And thank goodness that it sometimes acts as a photon, otherwise we wouldn't have photon torpedoes. So what is light? That was the question to begin with. Well, it's not a particle, completely at least. It's not a wave, completely at least. But as a matter of fact, light is just light. Why does it have to be one or the other? I'll give you an example of how we can think of that in a minute. Light has some of the features of a wave, and it has some of the features of a particle. Now, it's still that magic word. It's still electromagnetic. You had that memorized, right? That's important. And this helps us understand how science works in our attempt to understand the world. Because science uses models more often than not to explain things that we can't explain otherwise, or that are obscure to us. And we're not talking about models like that. We're talking about models like this. This, as you know, is a platypus. But what if you ran into somebody who had never heard of or seen a platypus before, and who wanted to know, he had heard maybe on the internet, there is this thing called a platypus. What is it? And it's up to you then to describe it and explain what a platypus is. How would you do that? Well, you might say, a platypus is an animal kind of like a beaver. Why is it like a beaver? Because it has a tail like a beaver. It's like a duck because it has a bill like a duck. Now, scientific metaphors are like similes in that very same way. We can use similes to explain a phenomenon without necessarily capturing everything about that phenomenon in one word. So, this is a platypus. It is not a beaver. It's not a duck. It's not even a duck beaver. It is a platypus. It is unique in itself. And the same is true with light. There are probably other things about light that we haven't discovered yet. But at least we know that sometimes it acts as a particle, sometimes it acts as a wave, and so we give it this wave-particle duality idea. Light is like a wave sometimes, it's like a particle sometimes, but it isn't just one or the other. The bottom line now is that in the 20th century, light can be modeled as a particle. Now, how does that compare to how light was described in Joseph Smith's day in the 19th century? Well, you'll remember that Maxwell had kind of concluded, and the whole scientific community had gone along with him, that light had to be a wave. What did Joseph Smith teach? Well, let's switch over now. We'll switch to the scriptures and learn something about his revelations relating to light. To do that, we need to get a kind of definition of light, and we'll find something important about light in D&C 84. There it says, "For the word of the Lord is truth, and whatever is truth is light, and whatever is light is spirit, even the spirit of Jesus Christ." So we see that these things, truth, light, spirit, are all related to one another. They're, in fact, by the way, this little sign doesn't mean equals, it means related to, okay? So the word of the Lord is related to truth, which is related to light, which is related to spirit. They're all related to one another. They may not be identical, but they're very similar to one another. And this provides us a key to understanding what light is about, what light is all about. Because elsewhere in the scriptures that I'm sure you're familiar with, in 1:30, he says this: "There is no such thing as immaterial matter. All spirit is matter, but it is more fine or pure and can only be discerned by purer eyes. We cannot see it, but when our bodies are purified, we shall see that it is all matter." Notice he's talking about spirit here. And from our previous reading, light and spirit are very much related to one another. So you could interpret, and I do interpret this scripture to relate light to these characteristics. That is, that light is a kind of matter. And when anybody talks about matter from the 18th, 19th century forward, we're talking about particulate matter. And we'll get back to this question about the particulate nature of light and matter in a minute. But the point is that Joseph Smith is talking about light as if it were a particulate material. And that relates better, as you can now see, to how we perceive light now in the 21st century, what its characteristics are and what it is, than it relates to what Clerk Maxwell was talking about light back in Joseph Smith's own day. So Joseph Smith's really talking about light in 21st century terms rather than 19th century terms. His statements agree with 21st century science, but not the science of his day. We will come back to this in a minute, but I want to introduce one other concept about light that I think is important for us. This one's a little bit more esoteric, so put your thinking caps on. I'm not going to present any math. Don't worry, but this is going to be important. I believe it is the idea that atoms are also electromagnetic. Now that is clear and easy and well accepted. Atoms are electromagnetic in what sense? In the sense that they are composed of electrical charges that attract one another. Electrons, negatively charged electrons surrounding a positively charged nucleus. You learned that back in high school, I'm sure. An atom's electrons can emit or absorb photons of light. And in fact, that's how atoms talk to one another. They exchange photons, and when they do, they change energy levels and so on. Light is used to transfer energy from one atom to another. So we have electron energy converting into photon energy and converting back to electron energy in the neighboring atom. And this is true for molecules as well. All of this really is electromagnetism at work. All of these processes are electromagnetic. Now, the word electromagnetic was not invented in Joseph Smith's day. So if you wanted to talk about this kind of stuff, you would use the word light. Each different kind of atom has unique electron energies and therefore emits a unique set of photon energies or colors. This results from the rules of a branch of physics called quantum mechanics, which is loved by all college students. For example, neon atoms emit a different set of colors of light than oxygen atoms do, and that's because the electrons in neon atoms have different energy levels than the electrons in oxygen atoms. And so if you take the light that comes from a neon lamp and you spread it out using a diffraction grating, wink, wink, you're going to see a pattern that looks like this. And in fact, I'm going to invite you now to pull out your glasses. I mean those diffraction glasses, right? Not your normal glasses. And take a look at the light that is emitted from this neon lamp. Now, with your diffraction glasses, you should see this kind of pattern immediately. With the little slides, you may have to look off to the left or off to the right. Can you see the pattern? Okay. If you're sharing with someone, please switch and let them take a look at it too. Is there anybody who can't see the pattern? Raise your hand. Don't be shy. Would one of you please, folks, go out and help these folks? Try to look, if you have the little individual slide, try to look off to the left or off to the right, and you should see the pattern. Okay. We good? Okay. Now you can see that neon has a different pattern of light than oxygen does. And that's one of the ways we can tell whether we have neon or oxygen. And we're going to have to move on now. So I'll switch this off. And we'll ask for the lights to come back on, okay? It's like a barcode, isn't it? A barcode for each of these elements. Would you please pass your glasses and slides now back to the aisles as the students come around to collect them? Here's a good question. How can you tell if there are oxygen atoms in a galaxy 10 billion light years away? You know the answer now. You just take the light that you collect from that galaxy, you pass it through a diffraction grating, you look at it and see if it has the pattern of oxygen or not. Oxygen, it turns out, is a telltale sign of the possibility of life. Why? Because oxygen is not a normal chemical component of an atmosphere unless there is photosynthesis taking place. The oxygen that you and I breathe wasn't here when the Earth was formed. This oxygen was generated by tiny microorganisms over a period of millions, billions of years. Oxygen was their byproduct of their biological processes. And so we benefit from the oxygen that was produced by algae many years ago. Okay, so I want to re-emphasize the importance of this word electromagnetism because it captures the relationship between atoms and molecules and light, and we can put them all in the same category. In Joseph Smith's day, these all would have been considered aspects of light. And as a matter of fact, for those of you who are physicists, you know that Einstein showed that matter itself, the normal matter that you and I are made of, is actually collapsed and condensed light. Let you think about that, E equals mc squared. At any rate, light is an electromagnetic wave particle according to science, but it's true for atoms as well. You could call atoms electromagnetic machines, or in 19th century terms, light machines. We are beings made up of light. How do we understand the world? Here's a brief description of how you understand the world. What's happening inside you right now to help you understand what's going on around you. You see some object that is emitting light. It comes to your eye as an electromagnetic wave particle or a photon. Your eye then converts that, the atoms and molecules in your eye convert that to an electromagnetic signal that passes through nerves into your brain. Within your brain, that signal then is processed using electromagnetic chemistry that allows you to think. So the whole process of perceiving and coming to understand what you're seeing has to do with electromagnetic or light processes. All our senses, sight, hearing, smell, touch, taste, they all work via electromagnetic phenomena. Pop exam, you ready for this? Light is an electromagnetic carrier of information between atoms, which are a kind of electromagnetic machine. And in 19th century terms, we're talking about light instead of this fancy modern term electromagnetic. So now, congratulations to you. You have studied quantum mechanics at Education Week, and you are now allowed to brag to your friends about that over dinner tonight. So what's the disconnect that we're trying to show has now been resolved between science and religion on this point, on these points? There are some. Turn your mind to D&C 88, and you've probably read this verse before, and maybe stopped and wondered what it meant. He's talking about the light that comes from the sun and the moon and so on. The whole chapter, the whole section of the Doctrine and Covenants talks about light at the beginning, the creations and knowledge and wonderful things. But let's focus in on this, on these verses. Which truth shineth? There is that connection between truth, spirit, light. Here we have truth shining. We normally think of light shining, right? But we're talking about truth shining. The same is true of light and spirit. This is the light of Christ, as also he is in the sun, and the light of the sun, and the power thereof by which it was made. And I want you to think, as you read these words, I want you to think about these electromagnetic processes that are happening in the sun that generate this light, that give it life and make it possible for that body of material to function the way that it does. But this is the important part here. And the light which shineth, which giveth you light, is through him who enlighteneth your eyes, which is the same light that quickeneth your understandings. This phrase right here leaves most people's heads scratching if they think about it. There seems to be an apparent disconnect because the science in Joseph Smith's day does not correspond to these ideas. It actually kind of sounds like gibberish on the surface. But if you think about it more deeply, and think about the sciences of the, not those sciences of the 1830s. We're talking about legitimate science of the 1830s, when atomic structure and the understanding of light was just in its infancy and being developed. Did we understand atomic structure then? No. Did we understand electromagnetism? No, the word hadn't even been invented. Did we understand how atoms and light interact? No. Now, the scriptures are not a science textbook, of course, but every once in a while you get an occasional brief allusion to a natural science topic. And that's what we find there in D&C 88. The word light is used, but as a matter of fact, electromagnetism is what's really at the heart of it from a scientist point of view. And so when we read the words, the light which shineth, which giveth you light, is through him who enlighteneth your eyes. So light comes to our eyes. It's the same light that quickens your understanding. Remember, we went back and talked about how when you see something, the light comes in, it's converted from one electromagnetic form, light, to another, an electrical current that goes into your brain, and in your brain, the electrons fiddle around long enough for you to figure out what's going on. That's what we're talking about here. That's what this verse, this seemingly obscure verse, is trying to say, I believe. That's the process right here. When you keep in mind that the term light is a one-syllable word that means the same as that big fancy scientific word. Now there's more in D&C 88 that we could cover. Which light proceedeth forth from the presence of God to fill the immensity of space, the light which is in all things, the electromagnetism which is in all things, which giveth life to all things, gives life to you and me. It allows us to work and function, which is the law, which is the law by which all things are governed, even the power of God who sits upon his throne, who is in the bosom of eternity, who is in the midst of all things. And so you have this picture of God centering the light of the universe, centering in God and emanating forth from him and filling all of space and giving life, light, and law to all things in the universe. This is a magnificent picture of what the universe is really all about. And it's consistent with the modern science concept that light, now termed electromagnetism, lies at the heart of virtually all the natural processes we commonly observe. Did you know that you are a being of light? You're a being of light in at least three ways that I can think of. First of all, you take in light. We've talked about this already. When you see a people coming out of the trolley in the subway, you see it because light bounces off them and comes to your eyes. That's one way in which you are a being of light. Normally, we see reflected light or light emitted from some other object. But there's another way that's really important that we don't think about very often, and that is that you actually radiate light yourself. You are a radiant being yourself. You are a source of light, because everything in the universe glows in some wavelength depending on the temperature. Even liquid nitrogen glows in some one of those kinds of light on the spectrum. We happen to emit infrared light all the time. You're emitting infrared light right now, all of you. And if you were to go into that same subway station and all the lights had been turned off and you had eyes that could see infrared light, you would still see all the people coming out of the train car, just like that. That's what they would look like. There's a third way that you are a being of light, and that is that your body is an amazing complex atomic machine powered by electromagnetism or light. This comes about because of all the complex chemistry that we see in our bodies, like DNA, for example. And I just wanted to illustrate for you a kind of awesome, this is actually a model of what's happening when DNA is reproduced as cells divide. I want you to take a look at this little reconstruction of how DNA polymerase works. These kinds of processes are happening inside our bodies, these electromagnetic processes involving atoms and molecules interacting with one another at speeds that you just can't hardly even imagine. This is slowed down. This complex of proteins here is able to process 1,000 base pairs on the DNA molecule line of nucleotides per second. Isn't that just amazing to think that that's happening inside you? That's what makes you work, that kind of thing. And there are thousands of different kinds of things like this happening inside your cells all the time. In Joseph Smith's day, there was an apparent contradiction, because we had this claim that the light that enlightens our eyes is the same that quickeneth our understandings, but it sounds like gibberish then, but it doesn't now. It's in agreement with latter-day scripture, you see. Scientists now affirm that electromagnetism, commonly called light, especially in former times, carries visual information to the eye and governs the chemistry of the eye and the brain, allowing intelligent thought. Light is certainly a topic worthy of study. And in fact, one of the best sources of understanding about light from a theological point of view, I have found, is in a little book that was published by Parley P. Pratt in the 19th century before he died, in 1855, that talks about a lot of different topics, but spends a fair bit of time talking about light and spirit and so on. We don't have time to go into a lot of what he published then. There's more of it in my book, but I'd suggest that we spend just a couple of minutes looking at what he said on this subject. There are several of these subtle, invisible substances, but little understood as yet by man, and their existence is only demonstrated by their effects, some of which are recognized under several terms: electricity, galvanism, magnetism, and so on. The purest, most refined, and subtle of all these substances, and the one least understood or even recognized by the less informed among mankind, is the substance called the Holy Spirit. Like the other elements, its whole is composed of individual particles. There's Einstein again. This is the great positive controlling element of all other elements. It is omnipresent by reason of its infinitude, and it pervades all things. It is the agent or executive by which God organizes and puts in motion all worlds. This is the true light which in some measure illuminates all men. It is, in its less refined existence, the physical light, which reflects from the sun, moon, and stars, and other substances, and by reflection on the eye makes visible the truths of the outward world. It is also, in its higher degrees, the intellectual light of our inward and spiritual organs, by which we reason, discern, judge, compare, comprehend, and remember the subjects within our reach. Holy Spirit, God's Holy Spirit, centers in his presence and communicates with and extends to the utmost verge of his dominions, comprehending and controlling all things under the immediate direction of his own will and the will of all those in communication with him in worlds without end. What a glorious picture we have there of light and spirit. In summary, science says electromagnetism, of which light is the carrier, powers and governs almost everything in the world around us and is foundational to life and intelligence. Revealed religion says God uses the light which centers in him to power, govern, and give life and law to his creations. It is the source of intelligence and thought. And one of the promises, one of the great concepts that we can maybe end with here is this: that which is of God is light, and he that receiveth light and continueth in God receiveth more light, and that light groweth brighter and brighter until the perfect day. That's our hope, isn't it, for each one of us?